Hi everyone, and welcome to our webinar today. We're going to be talking about the optimal design and operation of data centers. My name is Paul Bemis. I'm the president of Applied Math Modeling, and I'm thrilled to have with me today a good friend of mine, Magnus Herrlin. He's the president of Ansys Corporation. Magnus and I have gotten to know each other over the years working together in this field, and he's been very involved with the training in cooperation with the Department of Energy. So thrilled to have him with us, and before we get started, let me tell you a little bit about how this webinar works. First of all, we're going to work together, Magnus and I, to present the material to you. And in the interest of time, we're going to try to keep it to an hour. Now we have 2 data centers to review today, so things will probably move a little quickly. I am recording it so that if you want to go back and look at it, you can. I'll put it up on our website for review. Furthermore, in your little GoToMeeting interface that you have, there is a chat window that you can send questions to us. And we have found that's the best way to do it, as opposed to opening mics and possibly getting feedback. We find the best way to work together is for you to type the message. We'll address it and answer it for everyone. We'll repeat the question and answer it. So the other thing I'd like to say is there is a certificate if you're interested in a certificate of credit. Many of you are degree engineers or professional engineers, and you need occasionally to have professional training credits. This is worth 1 hour of professional training, and if you just send me a note, I'll pass that over to you after the session. So with that, let's get going. Most of you know who Applied Math Modeling is, but if you don't, we are responsible for the development and support and sales of the CoolSim data center modeling application. I have a background in engineering simulation. I'm a mechanical engineer and electrical engineer, and worked for many years at the Ansys Corporation as well as the Fluent Corporation. And I saw an opportunity to package the same kind of technology in a easier to use, more cost-effective way for occasional users. And that's who tends to use it in data centers, as occasional users. So we use a software as a service or SaaS model of delivery. And this allows you to pay proportionately for the use of the software and not have to pay as much typically because you don't use it as much. In terms of who we are, we're all experts in CFD and finite element and engineering and science. Most of us here at Applied Math Modeling grew up doing this kind of work and this kind of simulation, and my background's in hardware as well. I worked for Hewlett-Packard for many years building these computers and doing electronics packaging. So we're capable of modeling most any physical phenomena you want. Even if CoolSim can't do it, we certainly can. Now, let me turn it over to my friend Magnus. He'll tell you a little bit about his company and how he came into this. Magnus?
Thanks. Yeah, my name is Magnus Herrlin. I'm the president of Ansys Incorporated. And we are located in San Francisco, very close to Silicon Valley. So most of our clients, traditionally, are down in the valley. And we do environmental solutions for mission-critical facilities, that is, telecommunication facilities, and now more recently in data centers. Well, recently, during the past 10 years, actually, and before that it was mostly telecommunications central offices. So before that, I was working at Bell Communications Research. That was the research arm of all the Bell companies in the United States for 10 years as a principal scientist. So that gave me a really good foundation for starting working in data centers as well. Over to you, Paul.
Today what we're going to take a look at, Magnus, are 2 data centers. One of them is a non-raised floor design. It's got a floor-mounted upflow unit or units in it. So I thought I'd do one that is upflow and one that is a traditional downflow with a leaky raised floor. These are things that I run across. You know, we see a lot of models. These aren't any one specific model. They're usually adaptations of models I've seen go by or been interacting with. So no names here or anything. These aren't specific to a particular situation, but they are models that I have seen and thought it would be worth talking about. So I bring them up, and I use 2 different examples, and we're going to go through the same methodology. We're going to build a model using CoolSim. I already did that part to save time. And then we're going to perform parametric variations on it to optimize the design. We're going to adjust the airflow balance and adjust the supply temperature to try to optimize it for energy. We're going to work with a set of metrics called RTI and RCI. Magnus had an awful lot to do with coming up with these metrics. I think they make a lot of sense for this kind of work, and so I've incorporated them into the CoolSim product. And we're going to use them along with CFD analysis to determine what the optimal point is for each of these data centers. So Magnus, you want to, this is a lot of your input here. Would you like to just take us through the next couple of slides on air management?
Yeah, this slide just try to explain what air management is all about, and essentially it's about avoiding recirculation, and that's what they show on the left-hand side. That's when hot air is coming back over the racks or around the racks to the air intakes, and that's when you get hot spots that can knock out server equipment over time, or actually at the moment too. And then we have something called bypass. That's when we have too much cool air on the cold side, and it's going to spill over on the hot side, and thereby depressing the return temperature to the cooling system, and make the chillers less efficient. So both these processes should be avoided.
Mm-hmm. It's interesting to note that in the recirculation case, that happens when there's not enough cool air coming from wherever it's coming from, and in the bypass case, when there's too much. So having just the right amount is kind of key in this whole thing. So do you want to cover this one as well, importance of air management?
Yeah, absolutely. Traditionally, I think air management was about thermal management, and we've explained that. But also, of course, it's well connected with energy management. Like I said, if the return temperature is depressed because of bypass air, the chiller will not work as efficiently as designed. But maybe the most important today is capital management. Or recovery of capacity, for example, in a raised floor. Many raised floors are a little bit overwhelmed by flow rates today, and the main reason is probably that there is very poor air management in the space. So if you rearrange the space with good air management, you will notice that the capacity of the floor is coming back to you. And maybe you don't need to build a new data center because you have more capacity than you think in that raised floor.
That's right. That's right. And there's a balance here as well, right? The balance between energy and the thermal environment.
Right. I mean, it's hard to generalize because some organizations they probably emphasize thermal management over energy management. Take, for example, someone that's processing credit cards. Thermal management is extremely important because they don't want any surprises that the server goes down when there are transactions going on, and they're going on all the time. But maybe other organizations, like research organizations, they emphasize energy because their operations is not critical. If it goes down, it goes down, and many large federal data centers, they don't have any backup systems at all if the power would go out.
Mm-hmm. So I guess the goals here are for higher supply air temperature and lower airflow rate to optimize the servers. In the case of the higher air supply temperature, that's an energy issue as well, right, Magnus? I mean, if we get higher supply air temperature, we're going to improve the efficiency of the cooling system. And if we reduce the flow rate, we get two benefits from that. We, number one, reduce the bypass airflow, and number two, we also reduce the requirement for fan speeds. I guess the third one is, by definition, it increases the return air temperature because if the air rate is slower, then it has more time for heat transfer and therefore higher return temp, right?
Mm-hmm. Yeah, the important thing with this slide is really to show that not just two things you can change to improve air management, and that's a higher supply air temperature and or a lower supply airflow rate. There are no other parameters involved here.
Right.
Those are the two you can change to improve the conditions.
Right. Now, we're also going to be using a set of metrics here. Magnus was quite involved with the development of these metrics, and the first one is called return temperature index. This one is really a measure of net bypass air or net recirculation in the data center. It is a ratio of the rack flow rate divided by the air handler flow rate. At least that's how we tend to look at it in the CFD business. It's a flow rate issue. It's also a delta T issue because the equation is flow rate is correlated to delta T, of course. But we tend to use this one up here. And the easy way to determine how much flow rate you need in your data center from the cooling units is to just take the load, take your total rack load, and multiply by roughly 156 cubic feet per minute, and you'll determine exactly what that air handler flow rate ought to be. Now, what I often find is that it's much higher than when the rack needs, and that's for a couple of reasons. Number one, the data center is probably not running at its maximum capacity, and the air handlers were built for maximum capacity. So oftentimes when I enter a data center, there's way too much air for what the rack requires. Mm-hmm. The other part is that just because you have the right amount of air coming into the room doesn't mean it gets to the right location in the room, and that's back to the issue of air management. Mm-hmm. But a perfect system is when they're completely balanced, when you have just enough air coming into the room to satisfy the needs of the racks and nothing more. If you have too much air, it's going to drop below 100% and you're going to get bypass airflow, which means it goes right back to the cooling unit. If it is greater than 100%, it means you don't have enough and you have starvation, and the racks start to breathe their own exhaust and get hot, and you have hot spots. Mm-hmm. The other metric here that we're going to be using today is rack cooling index. This is a measure of conformance, really. Do the rack inlets conform to the ASHRAE specification? Specification is in Fahrenheit 64.4 to 80.6 for recommended, and 59 to 89.6 for allowable. Now, a lot of studies have been done recently that says that anything beyond 77, 80, in the range of 77 to 80 degrees, the servers begin to kick up their fans, and so you hit a point of diminishing returns because the fans start to speed up as the rack inlets go up. Mm-hmm. So most of us use this recommended range here, 64.4 to 80, as a way to determine whether or not our rack inlets are in compliance. And without going into the mathematics here, it's sufficient to say that both your RCI high and low should be in the 95 to 100% range. You could get them there. RCI low is looking at the conformance of the low temperature range, how many of them are out of compliance or in compliance. High is looking at the high temperature range. So these two metrics help to boil down the results of, in our case, CFD runs to a couple of metrics. These are indices, they're dimensionless, and they allow you to understand where you are with respect to optimization of the data center. So those are two more that we'll be using today.
So Paul, maybe something we could add there is that the right way to do this is to look at these two metrics, or these three metrics at the same time, because when you're changing one, you will change the others.
Right.
So you want to tune in to a balance that you feel that is appropriate for your organization, and that's exactly what you're going to show here later on.
That's correct. We're going to use them for optimization because they do interact with each other in an interesting way. So what we're going to do here is we're going to create a model of a CFD model of a data center. And by the way, when you're building these models, my recommendations are to avoid the little stuff, the small details that don't affect airflow. Whenever you're doing modeling, we have to focus on the dominant parameters. This is a mistake that's often made early, is that users often try to put too much detail in too quickly. But the dominant parameters in the data center are going to be geometric placement of things like racks and cooling units and things. It's going to be height of the room, height of the plenum, ceiling. It's going to be where the air handlers are and how big they are and what they're operating. And I typically start with average watts per rack. Now, it's not perfect because if it's a 10 kW rack, where's the 10 kW? Is it high? Is it low? You can do that in CoolSim. You can get into the rack and model it all the way down to 1 U of density if you want to. But I recommend you do that later. Oftentimes in simulation you can get lost in all of the data if you're not careful, so it's important to pick the big parameters first, zero in on those, understand what the big parameters in the room are doing, how they affect things, and then dial in later on if necessary to bring it to a finer point of resolution. The governing equation for all of this is the convective heat transfer equation shown here. It is heat transfer is mass flow rate times density times specific heat times delta T. The delta T is the return supply delta T. The same equation is the governing equation for the cooling unit as it is for the rack. And in particular, if you have your delta T's equal, the average delta T of the racks are equal to the average delta T of the air handler, then you have a balanced system. Your RTI is 100%. So the steps we're going to use today for optimization are step one, we're going to go for RTI. We're going to adjust the air handler unit airflow to match only what is required by the racks. So we're going to drive the RTI parameter towards 100% until RCI high, which is measuring conformance, begins to decline. So what I mean by that is if the RTI is low, that is to say you've got much more air handler airflow in the room than the racks need, then the chances are you're not going to have any hot spots because you're overcooling the place. And by the way, the return temperatures are usually going to be awful and you're working the system really hard and it's just suboptimal. But you won't have any hot spots. Your energy will be high, energy consumption will be high, but you will likely have hot spots. But what we're going to do is begin to turn down the air supply. And that would drive up the RTI until it gets to 100%. But as you begin to take air out of the room, sometimes RCI high begins to decline, which means you've got some hot spots. You can see them in a CFD model. That's the beauty of modeling, is you can see now where they are. You can implement air management as necessary and then do it again, run it again. And what you find is, oh yeah, the hot spots went away. Now I'm all set. I may have a little bit too much cold going on. So then you can begin to push supply air temp up. That's where your energy savings really comes from. I shouldn't minimize the airflow energy savings as well. Remember that these are fans, and the power of a fan is cubic in the sense of power savings. So if you reduce the fan, the amount you reduce in an RPM, which is correlated to power, generally improves the efficiency by a cube of the ratio of the RPMs. So that's a big piece, and I don't want to underestimate fans themselves. But as you drive up the supply air temperature, which in turn drives up the return air temperature, you also get efficiency savings, and you get equipment life out of it too, because the chiller doesn't have to work quite as hard. So we're going to use these steps to optimize a data center. Now, this is a little chart that I made to show sort of the effect I was talking about. RTI often starts off low because we're supplying too much air to the data center. RCI high is not a problem because we've got too much air in the data center, and oftentimes this is because the data center isn't full and it was built to handle certain capacity and you're only at a fraction of that capacity right now. So you're in a situation shown over here on the left. RTI is low, RCI is high. And then as you start to turn down the air handlers, the flow coming into the room, you'll start to climb the RTI curve. It'll go up, and at some point you'll hit an inflection where RCI high begins to decline. That point where it starts to decline is a result of the fact that in this scenario we don't have perfect air management. And so before I can get to 100% of RTI, before I can get to an even amount supplied is equal to the amount required, I start to run into hot spots. And that's exactly what that is showing as it rolls off. So our goal in this next example is to find this point and then to push it to the right by doing air management techniques, and therefore get RTI as high as we can and RCI high as we can. This will by nature, by definition, take care of RCI low and should give us an optimal operating point for the data center. Is that well covered there, Magnus? Anything you'd like to add there?
No, I think that just said it.
Okay. So we're going to drive RTI up until RCI starts to decline. So the first data center we're going to look at is a fairly small one, 1,500 square feet. It's got two 20,000 CFM upflow cooling units. It's an N+1 design, so it's designed to run with just 20, and that's how we'll be modeling. We'll be modeling in an N+1 design. This is a naturally convective hot air return system. It's only a 71 kW data center. I'd like to point out that CFD modeling is not exclusive to only big data centers. It's very helpful in small data centers. In fact, often more helpful in small data centers because you've got less volume and more room and things are swirling around even more vigorously than they might be otherwise. This design is not an air handler in the sense that it's got an outside chiller. So this one is an on-off state. So we're going to shut one of them down and just look at it when it's running under a one unit. This is a shot from the CoolSim 4.4 modeler. This is what the model creation process looks like. You see here the racks. The green indicates direction of airflow. These are front to back. You can see this is a hot aisle here. Here's another hot aisle here. This one's kind of a mess over here. It's blowing into this one. So guess what? Not everything is perfect in these data centers. These are two upflows. This is a very traditional upflow, which always confused me because the air is returned at the bottom. Normally they're returned at the top, but these are returned at the bottom and they blow up. This one's blowing up into a ducted system through some ducts. Now in CoolSim 4.4, which was just announced today, you can build these ducts and modeling will flow through these ducts very quickly and efficiently. So the cooling return or the crack return is right here. This is a PDU in red. These are IT racks right here. Now, if we take a look at the energy report that comes out of the CoolSim system, when you run a job, it shows like this. The COP here, this was an assumption. By the way, in CoolSim right now, you do have to make an assumption about the baseline COP. COP is the coefficient of performance. It's simply a ratio of the amount of energy required to reject the same amount of heat or a amount of heat out of the room. So the COP is 2, which means that it's taking 1 kilowatt to reject every 2. That's not a great number. 4 would be better. The chillers often run in the range of 4 for every kilowatt they reject of heat. They require about 250 watts to drive them. That's a fairly good ratio. This one's not a good ratio. It's 2. These are often a result of being DX units, but also this one's got a very poor return air temperature as well. So that is an estimate. To be honest, it doesn't really matter so much about what that baseline COP is. What you're talking about here is a percentage improvement. So one thing to remember is percentages work very well. You can assume a baseline and look for a percentage improvement, and then whatever it's costing, you'll save that percentage the following year. Other numbers here, the PUE is 1.74. Here's our, and DCIE is 58%, just the inverse of PUE expressed as a percentage. RTI, 55%. There we go right there, Magnus. A little bit too much airflow, I'd say, right?
Mm-hmm.
RCI high is 100. We don't have any hot spots. RCI low 9. We're too cold. So
well, that's the point here, Paul, that if you look at this RTI, RCI high and RCI low, you can see now how they interplay, because RTI is very low, meaning that we have a lot of airflow coming into this data center. And that the consequence of that is that the RCI low will be very low because we're overcooling. So we have too many temperatures too far down in temperature, whereas the RCI high is fine because naturally we have cooled down this whole data center, so there are no hot spots left.
Yes. I'd like to also just point out here that if you're running very cold and you have cold return temperatures, one of the things that you run into right away is that the capacity of your cooling system degrades, it declines. These cooling systems, whether they're, and oftentimes you buy them based on a tonnage, that's the old English system. So say if it's a 4-ton, nominal 4-ton cooling capacity unit, well, that assumes that the return air temperature is in the 80s. If it's not, then it's not a 4-ton unit. It's much less than that, and it declines pretty quickly. Furthermore, it has to run a lot harder, and that means energy, and of course, it reduces its life. So now, this is some output from CoolSim right here. This is, in fact, the exact output that came out of this model. And in CoolSim, what you're able to do, and I'm able to show you the entire set. I have two runs here, run 0 and run 1, done off the same model. And you can put the entire set of output of CoolSim into a PowerPoint presentation as I'm showing you here, and it makes for really, really nice viewing and really easy way to look at results is what I find. So if we take a look at the summary report here, and in particular look at this energy report, we find just what we saw, RTI at 55%, RCI 100, RCI low of right around 9. And if we go a little further here and we look at our crack performance report, we'll see that we're returning terribly low temperatures. We're driving it at 55, we're returning 67. That's just really hard on a cooling unit to return that low a temperature. You really want the returns to be, well, if the inlets are near 70, you want the returns to be 90. You want a 20-degree delta across your crack unit. And, you know, preferably move it up so that the return is up in the 80s, 85, 90. In fact, the converse is also true. The higher the return temperature, the more efficient the cooling unit is, and its capacity actually grows. It gets to the point where a 4-ton crack may become a 5 or a 6 because you're returning very high air temperatures. So we can see this model here. There's also a number of plots, but they're fairly straightforward. This one is a conformance plot. Here I'm looking at temperature as it conforms to the ASHRAE spec. There's the spec right there, 64.4 to 80. And you see it's actually failing. It's too cold. So we've got some of the rack inlets. These are just the inlets. Some of the rack inlets are supplying air too cold. Other regions are okay. And that's because there's a tremendous amount of air swirling around in this room, coming from the cooling units and down and just swirling everywhere. If you take a look at these path lines, you can see the air. And in this data center, what's happening is the hot air, and this is hot air here, is flowing out of the back of these cracks. And you see we put arrows here now on the newest release of CoolSim so you can see the direction and the temperature. So we're watching this air come across the room and have to go all the way back down and be sucked in. And you can see what happens is as it comes across hot, you see the color moving to cold, because as it gets near the bottom where the high density cool air is sitting, because it's heavy, it mixes and it causes the return temps to cool off. So this is a fundamental problem. I see this a lot in these kind of data centers, and that crack unit may be rated for a certain capacity, but it's certainly going to run well below that rated capacity. There's also a series of animations here that get built that show the sequence, but in the interest of time, we'll just move ahead. So now what we've done here is we're going to increase the RTI until the RCI starts to decline. So within CoolSim, you're able to take a look at different scenarios based off the same model. So again, this is just output. I'm looking at the output. You can view CoolSim output without being in the modeler. So I've exported the output, and you can view it in HTML and web pages. So you can see here in run 0, I went to 10,970 CFM. I dropped the RTI. Actually, I increased it, but I dropped the supply flow down and began to run at a flow rate that's much closer. In fact, I think that's just about spot on what the rack needs. So let's see what happens. Now, I did this in two different ways. In run 0, I shut crack 7 off, and in run 1, I shut crack 8 off. The reason we do this is because in a system where the only way you can modulate airflow is to shut one unit down, you have to understand the flow conditions under both states. In other words, if unit A is off, what's it look like, and then if unit B is off. This is also true in crack failure analysis. You want to understand what happens when a cooling unit, an air handler, goes down. You have to model it to understand the flow pattern in the room. So let's look first at unit 0, and let's go first of all to the summary report. We'll go to energy again, and you see RTI spot on, 100. RCI high is 99.85. It looks pretty good right there. I mean, that's certainly a good situation. RCI low, yeah, still not quite there. Okay, and if we take a look down at our crack performance report, we're still pumping 55-degree air. So it's still just too cold. So now we're headed in the right direction. We've moved RTI up. That's good. We've got the airflow rate working correctly now. But what do we do here? How do we get RCI high to stay there as we move up RCI low? This is going to now be a temperature issue. Can we raise temperature? And if we look at the recommended, we're getting better here, but look what's beginning to happen, Magnus. We're beginning to get a little bit of tearing right there. Mm-hmm. And we're at 55 degrees of air supply. What's kind of interesting about this is you see that plot, and then if I go to run 1 and I look at the same plot, you'll see slightly different characterization. You see it moved. It moved over to here. Right. Where it was over here before. And if we look at the numbers, they may have moved just a little bit as well. They shouldn't move much, but they move a little bit as well. Mm-hmm. So we've got the RTI in place. The question then became, what else can we do to improve it so we can drive up supply temperature just a little bit?
But so one thing we could point out, Paul, is that if you compare those numbers, those metrics with the original case, we have improved everything significantly just by pulling back on the airflow.
Right.
So there's a really big change here, much better already. Yes. But of course, you're going to show that you can fine-tune this now.
You can go a little further. So what I tend to do is I turn the RTI up, specifically the incoming flow rate down of the air handlers, until I start to see some RCI high problems, and then I look for opportunity to improve air management. And in this model I did two things. One is I put these snorkels onto the cooling units. A snorkel is the idea of putting a duct up into the air where the hot air is. The hot air naturally floats to the top of this room, and I want to go get it before it cools off. So these are just ducts. This is sheet metal. It's not very expensive. And you put these on the front, and it pulls the hot air down from up on top. The other thing I did is encase just one of the racks. This is a curtain. You can do these in many different ways. They do not have to be insulated. They don't have to be adiabatic at all. In fact, oftentimes curtains can work just fine. You do have to worry about fire codes a little bit when you do this, but it's a practice that is used quite a bit. So I put some curtains in place to force that air up into the upper end of the room there. And now let's just go have a look and see what that did. So here we're going to look at the same set of runs. Let me just show you what the return paths are doing now. If we take a look at the air coming out, you see it's going straight up into the top. And it's being sucked down that snorkel. You can see this one is on in this case. You can see that hot air coming right down there. And in this version of the viewer, I believe I can shut off here some of this room so you can see a little bit clearer. So that's a pretty good shot right there that you can see of the air now coming down, and it's yellow. It's in the 90s. This is a good sign. If we take a look now at our summary report, I'm sure we're going to find that our return temperatures are in much better shape than they were before. So under crack performance, ooh, look at that, Magnus, 96 degrees. I've got a nice delta T right there, and I've moved the supply air temperature up as well. The average supply air temperature 75 degrees, return 96. That's pretty nice. Now I'm looking at run number 3. I didn't start there. On run 0, and there's a summary right here of the various states. So in run 0, I started 11,000, which is just about an RTI of 100, supply temp 60. And then on run 1, I started moving up a little bit, 65, assuming that I was going to be in good shape over here. And then on run 2, I went to 70 degrees. I stepped up another 5 degrees. And on run 3, I'm running at 75 degrees of supply air temperature. So in this run, I've got 4 different variations here. And let's go have a look at them. So run 0 is the first one. I'm sure if we look at the energy report, we're going to see COP improved to 3. We've got RTI now of 99.97, and look at the other two. High and low, both sitting there at 100. That's a good-looking representation, huh, Magnus?
It's sweet.
But I think we're going to find, if we look at our crack, that's where I'm cold. So there's 60. We went up to 60. We've got an 81 return. At least we're in the range of spec now for the crack units. Let's see what happens as we march forward. So here's run 1. Same exact scenario. Let's look at our data energy report. 99 again, 99, 100. You see we're just starting to back off on RCI high here because we moved temperature up.
Mm-hmm.
So that's heading towards optimization. But look what we did to the crack units. If we look at the crack unit supply and return, we're supplying at 65, so we've gone up 10 degrees from where we started. We started at 55. We've gone up to 65, and we're at 86. And if we look at our compliance, still pretty good. We've got one small area. And I think, Magnus, you know, we don't want to push for RCI high to be 100% all the time, right? I mean, because this is real life. This is an approximation, I would argue, right?
I think staying in that 95 to 100 is a really good target, but many decide to stay at 95 because they can back off on that requirement a little bit and save energy instead.
Yep. So here's a summary of what we did, and I continue to go. In the interest of time, I'll just put this plot up here, or this chart up here, because there's another data center I'd like to get to as well. But what we did here is, and I put it in summary form, we started off with case 1, no air management, and case 2, no air management. What we did initially is we drove RTI up, okay? And we did that by reducing the amount of air coming out of those air handlers, or in this case, air handler is just one of them. We assumed in this case we can modulate that flow. It does depend. If it's a chilled water system, you can modulate it easily. If it's a DX, a direct expansion unit, you can't modulate that airflow much other than to turn it on or off. Newer systems do allow you to modulate it 30-40%. And that's all we've done here is modulate it 30-40%, so not too bad. So we drove our RTI up, but you can see what happens is the RCI low is too high. So there we started to say, okay, we need a little bit of air management. So with air management put in place, now we're able to drive supply air temperature up to 60 degrees. All right, and these guys are still holding. So you've got RTI at 100, RCI high, and now RCI low came up. So this is a very nice case, case 3. And then I took one more step, Magnus. I said, well, all right, let's drive another 5 degrees. COP came up yet again. Okay, so COP now 2.4. And RTI 100, RCI high 99, RCI low of 100. So you see right here is that tipping point. This is the optimal case. I'm running with 65 degrees of supply air temp. We saw the return temperatures were very quite high, nice 20-degree delta in the high 80s. The COP actually increased, and that's because the efficiency of the system got better as we increased supply air temperature. We reduced fan speed, which saves money as well. Total facility power dropped. PUE dropped. We have PUE declining all the way across here as we reduce energy consumption. DCIE got better, which is just an inverse of PUE. RTI high 100, RCI high 99.6. And we calculated here the annual savings to do this would be about $16,000 a year to save on an operating data center of about 100K. So looks like about 16% savings per year. And all we really did here, Magnus, is modulate the airflow and put in some sheet metal. So I think the changes...
Something else you could point out, Paul, is that going from the base case to the case number 2, we didn't invest a single dollar, but we just actually turned knobs, and we actually improved both PUE, RTI, and RCI high and low in one sweep. And then when we actually spent some money to put in a little bit better air management, we reached a really good point where actually we demonstrated that when you do air management, you don't have to compromise energy or reliability. They can go hand in hand, because the 4 metrics in case 4 are all better than in case 1 or the base case.
Yes.
So if you do it smartly, you can improve both energy management and thermal management.
Right. And this technique, this method allows you to know which way to go. It basically is a guide. I mean, already we have had a question come in already, Magnus, about accuracy. How accurate is CFD modeling? And it's a question I often get. How accurate is this stuff when compared to the real world? Well, it's very accurate when compared to the real world. Another way to say it, I think, Magnus, is it's as accurate as you want it to be. In other words, if you want it to exactly represent something that is existing right now, you can certainly get it to do that. This science has been around now for 30 years. It's well understood stuff. There's nothing here magic. We're just doing physics on air. All well understood stuff. It's as accurate as you want it. The point that I'm making here is that the best use of this kind of tool is as a tool or a guide to let you understand more quickly what needs to be done and what can be achieved. It is not a forensic tool to be used to determine the current state. Building a model of a current state is only good in the sense that you have a model that accurately represents the current physical phenomena. What these tools are good for is predicting the future, predicting what will happen in a future case. And there's no other way to do it. You can't go into the data center and experiment. That's not very effective. So
another word about the accuracy.
Mm-hmm.
Well, the accuracy depends on the skills of the modeler and the software tool itself. And if you do a sloppy modeling, the absolute numbers will not correlate too well with reality. However, even in that scenario, if you do permutations of your design, the trends are usually quite accurate anyway.
Correct.
So that's a good thing.
Yeah.
For example, in our case here, when Paul did 4 cases, even if he had done a sloppy job of putting this model together, I'm sure he didn't, but if he had done it, these trends will still be quite true.
Yes, that's correct. For example, one of the assumptions I made in the base case was that the racks were evenly distributed with power and that they were blanked properly. Not always the case. But regardless of how they are today, the trend, as you pointed out, the trajectory of improvement will follow what we're suggesting here. In a real world, we'll be able to get it to 65 degrees. Well, no, but we can certainly get it off 55 degrees by following these techniques. So, as you point out, it's used as a tool to guide good decision-making in the field. So let's look at another design. This one's a little bigger. This is an 8,000 square foot room. It's a raised floor data center, downflow in this case. Return plenum height, 4 feet. And this information comes right from the pre-simulation report that is part of CoolSim. I just dumped it into Excel and put it here. So this is a summary of the input side. A little bit more here about it. We've got 4 cracks, 80,000. They're 20,000 apiece. Total demand, 56. So again, this one was built for an N+1 case is what I suspect. And in an N+1 case, you can see that's running pretty much at capacity. N+1 would be, if one of these guys was down, you'd be running 60,000 at 56. So now, when they're all up is when you have the issue, of course. When they're all working, you've got an RTI that is way too low. Yeah, this is the summary of this data center, and here's a shot of this one. This is a very typical data center I see a lot. It's in a process of evolution. You've got most things in hot and cold aisle configuration, but you can see the ceiling tiles here are certainly misplaced, and you've got some equipment like this one right here where the air is pointing at 90 degrees to everything else. And there's a couple of classroom style here. If you look closely, you'll see the airflow direction on these is out and right into the the cold aisle input of these. So this is what we call classroom. The inlets are all facing the same direction. But this is a hot aisle here, or a cold aisle. This is a hot aisle right here. These are actually facing each other, so that they did make a hot aisle there. Very typical kind of situation that I often encounter. So we'll take a look at this one. Here's again the base model. And in this base model, we can first take a look at the summary report. So let's take a look at our energy report, and you can see RTI of 70. I mean, right away we've got problems, and that's because it's an N+1 data center, but all 4 of those units are running full tilt. They're running full blast. So if we look at our data center description here, we'll see that we have probably the racks want 56,000, we're delivering 80. So there's the problem right there, 80 on 56. And things sort of cascade from there. You know, the return temperatures on the cooling units become low. The RCI high is good. I mean, we don't have any hot spots. To be honest, we've got a little bit of hot spot, which makes me surprised considering how much air is in the room. But again, we run into the same problem. RCI low is 37. It's too cold. We take a look at our rack inlet plot here. This is again a plot of conformance. We see a very typical pattern, all the colors. Remember, blue is below spec, and red is above spec, and green is within spec. So we're mostly too cold in this room. Supply air temperatures here, let's take a look at our supply air temperatures from our crack report. Here's our crack report, 60. And look at the return temp, 73. I mean, again, a 13-degree delta. Here we got an 18-degree delta. That's a little better. But running in this range of supply of return air temperatures is really problematic because it reduces the capacity of those cooling units. So most of the other plots there are fairly, I mean, one of the ones that you can look at here is the flow rate on the tiles, or, oh, I know what I wanted, path lines. Path lines from the racks. This is very typical in terms of your path lines. They're just going everywhere. So this is a very typical situation, and you see some breathing right over the top being sucked over into the intakes of others. So this happens quite a bit. It does have a return sealing plenum. That's a good thing, but there's a lot of mixing going on in that room. So what do we do? Again, adjust the air handler airflow to match what's in the racks. Now in this case, these are chilled water systems, so these are air handlers. So we're able to modulate them with fans like an EC fan or a variable speed fan of some kind. You can bring them all down together. That's preferred because it's better from an energy point of view to bring them all down a certain percentage. And then again, we do that until our RCI high begins to be affected. Then we implement air management as required and then begin working on supply air temp and find the upper limit. What is the optimal design point for this data center? How low can I run the flow, the airflow coming into the room before the racks get hot? And how high can I run the supply air temp before the racks get hot? A rough rule of thumb is for every 1.8 degree increase in supply air temp, you get about 3.5%. Some people like to think about that as 1% per degree. It's not not too far off. It's a little better than that actually. And this tends to hold up fairly well in the range that we're talking about. It's not a linear relationship, but in the range that we generally operate in, it holds up fairly well. So let's take a look at this one. And we've got here, let's look at our summary. So I did 2 runs this time. And oops. The first run, I ran it at 175 CFM for all of the cracks. I brought them down just a little bit. Remember, they were at 20. So I brought them down. I'm driving RTI to 100% here by going to step at 17.5 and then a step at 15. Step at 15 equals 60. The racks demand 57, so this one's going to be just about 100% RTI right here. And the question we're going to ask now is, what happened? How did it perform? So let's go to run 1 because that's the one we're really most interested in. That's where the RTI is the highest. And again, I'm just trying to save a little bit of time here in interest of our webinar. So let's take a look at the summary report and let's take a look at data center energy. And we have RTI at 94, not too bad. RCI high, 90. Okay, we've given up a little bit here. As we increased the RTI, we gave up a little bit on RCI high. Magnus, this is to your point. This is the interaction between these two becomes the first place you go. How high can I drive RTI before RCI starts to get in trouble, right?
Mm. And also we can add there, if it's impossible in one particular design to get these to go in the right direction, the reason is most likely that it's very poor air management in the space.
Mm-hmm. And you can see that right here on our recommended plot. These are rack inlets. And you can see again what's going on. Same issue. Now, it's in that region I was talking about before. A couple things about that region. Notice that these racks are aligned with each other. So, you know, this is an inlet. So we've got an inlet here, and chances are we're recirculating. The other thing about that particular design right there is there's not a lot of perforated tiles that I notice. If we just look at the geometry alone, which is shown here in this representation, we'll zoom in a bit here, and I'll show you that there's no perforated tiles really there either. So I'm not exactly sure why, but in this region right here, we don't have enough perforated tiles. There's also pipes and so forth under the floor there, so that's going to be problematic as well. But certainly adding some perforated tiles there would be helpful. So we've got an air management issue that we have to deal with, and so what I did in terms of air management is added some curtains. I added them over here on the left because it was just easy up against the wall, and I added them in this range, in this area right here. And I had to separate this aisle and put a curtain around it and drive that hot air up into the ceiling right there. Put a couple more perforated tiles here and put some curtains around this section. So you can do this piecemeal. You don't have to do containment all at once. You can say, I need some over here. Let's see what happens if I put it in place. Again, it doesn't have to be rigid, expensive, kind of stuff. It can be curtains. It can be, I've seen people use plexiglass and just use big magnets and use plexiglass on the end of the aisles. And I've seen people operate pretty effectively with that. So it doesn't have to be expensive and it doesn't have to be complicated. It just has to keep the hot and cold from interfering with each other. Now in CoolSim this is easy to model because you can slice right through the cabinets with a baffle. So you drag this baffle into the room and you see I've just let it slice right through the cabinets. As long as it doesn't block the inlets and outlets, it'll be fine. And these racks actually are front to top and rear, so I had to bring them near the front. This is actually the front here. Put those curtains in place. But it's a very quick thing to do in a modeler. You can put them in extremely quickly and make a run and see what happens. So here's, after we did the management changes, this is what I did. Now you can in CoolSim run up to 4 variations at once. One of the nice things about having a common cluster that we all run on, I mean CoolSim is client server and the server is a big HPC cluster, you can run multiple variations concurrently. So in this one I ran 4 variations, 0, 1, 2, and 3. And you see I marched up again the curve of RTI. I started back where I was at 17.5 and 60. And then I went to 15.5 and 60. That's where we ran into trouble before. And then I stepped again. I went 15.65. And then I stepped again and went 15.70. Now 15.70 is pretty aggressive. And I suspect that one is probably outside the bounds of capability or ability, but let's take a look at run 2. This one is going to be at an RTI of just about 100, 65 degree Fahrenheit. Let's see how that one comes out. And again, we go for the summary report, which is the text-based report. The output is always the same in CoolSim. It comes out in this format each time. There's nothing unique I have to do here to get this. See, our RTI is at 94. That's pretty good. It's probably as good as I'm going to get. RCI high at 93. A little bit lower than I'd like. If we take a look, we're probably getting in trouble near the same area. Yeah, of course, there it is. These racks are having trouble despite the fact I put some containment around them. They're still having a little trouble. They still don't have floor tiles in place, so one more optimization step would be for me to go in and put some floor tiles in place there and here. So the model will actually give you guidance as to where to put your floor tiles and how to set them, where your trouble spots are. And you'll get a feel for the room by running the model. Let me step back one and look at run number 2. In run number 1, Run number 1, if you remember, we ran at 60 degrees, I believe, here. Yep, 60 degrees is where I really stopped the last time. And let's take a look at that one from an energy point of view. So we'll go into our summary report, look at energy, and you see there my RTI is 94, but my RCI is 99. So temperature made a difference. I'm holding RTI constant here, Magnus, and this one's at 60 degrees, and then as I step to 65 degrees, that one drops down just a little bit. Mm-hmm. So it looks like that's our optimal point.
Right.
So there we are right there at 93. So by going from 60 to 65, we drop down to 93.68 on RCI high. Not too bad. I mean, we're still in the high. And then you have to look at your plots and see, you know, how much does that really affect things? Do I have equipment up that high? Is the density really that high as the way I've got it modeled? Again, this is a guide, but at least now we know exactly where we stand with the design. And again here, I just took that information. You can take those summary reports and drag them into Excel, and that's what I did here. I created an Excel spreadsheet. And you can see here at 65 degrees, my RCI high comes down a little bit, 94. So we go from near 100 down to 94. And that, of course, is, no, we stay at 94, I guess. No, RTI, here it is, RCI high right here, 100 to 94. And then if I jump up to even higher, this one's at 70 degrees Fahrenheit, it falls off altogether to 74. So again, here's the optimal operating point, right here, 65 degrees, 60,000 CFM, and if I can get the system to operate that way, my coefficient of performance improved because I went up 10 degrees, so I got another 10% out of that. I went up 5 degrees, got another 10% out of that. 10 degrees will get you roughly 20%, so that feels just about right. RTI, DCIE is 71, RTI 94, 94. We came up on RCI low, we got out of the cold, which gives our equipment longer life and reduces its energy consumption. And with those implementations, we are estimated to save about 10% per year. I mean, again, these numbers are estimates, but you can say clearly, well, based on our base case, 10% is going to be easy to get. That's, in this case, 50K. That's a fairly good number. Thoughts about that, Magnus?
Yes, I think that shows pretty well how this optimization is supposed to be done.
Mm-hmm. So just a quick set of summary steps. Build a model. Go for RTI first until RCI begins to be affected. Use air management techniques to improve the issues you have in the hot range. Go back and turn up your supply air temp as much as you can before you run into trouble, and at least you'll know where you belong, where you're supposed to be in that data center. Now, I'm sure that a lot of you have questions and so forth. Let me take a few of them. And if you do have a question now, please type it into the chat window that's with your GoToMeeting session, and I'll talk it over and we'll have a look at it. The first one is...
Paul, can I interrupt you for 1 second?
Absolutely. Go right ahead, yeah?
You know, I forgot to say that when I introduced myself, but, you know, the U.S. Department of Energy have invested a lot of money into developing a training program. It's called the Data Center Energy Practitioner Program, and it's a 1-day or 3-day training program, and actually Paul has gone through that training himself.
That's right.
And this program is called DCEP in short. It's DCEP, and if you go to any search engine and type in DCEP, you will directly see this program popping up. And for those of you that feel that you're a little bit uneasy about air management, that is an excellent training program for understanding these processes a little bit better.
Okay, I'll put it also in your chat window. I'll type it in. The Data Center Energy practitioners program. And so I just sent that out to you all. That's the name. You can Google that, and that will take you to the training material and to the courses and when they are. Here's a question. Based on average watts per rack, how many adjustments are required to get the model correct?
Mm-hmm.
Not that many. I mean, again, it's a guide. It depends if the rack is blanked or not. If the rack is blank, so there's not a lot of leaking, and there's holes between the servers, then average watts per rack is pretty good. The next thing I do, if I'm in a data center and I get a chance to look at it, I just stare at the rack and guess how many servers or see how many servers are in it. If I know that the watts per rack is, let's say, 10, and there's 4 servers and they're in these slots, then I'll go in and put that detail in place. Mm-hmm. Easy enough to do in CoolSim. We make it very fast and easy for you to lay out where the wattage is in the rack. So I usually divide pretty evenly. You don't have to kill it in terms of detail to get good advice out of these systems. The next one is, what's the best technical resource you recommend to understand the physics of computational fluid dynamics? The best technical resource, Magnus, for understanding CFD? Well, there's a tremendous amount of material out there about it. Not hard to find. Do you have any recommendations for sources on CFD? I always think of the textbooks I learned in school, of course.
Mm-hmm. Well, it depends a little bit what they mean by understand. I mean, are we talking about the physics or how you apply it?
It says the physics. Understand the physics. This is from Jean Fontaine. The physics are fairly straightforward. It's using CFD and understanding how to apply it maybe would take a little time. I don't know. You have any thoughts on that?
Yeah, no, I would suggest to go to a search engine and type in some well-selected words for finding that particular information. I'm sure it's going to pop up right away. Yeah. If you can say like practical, description of what CFD is all about, it will pop up right away probably.
Yes. There's also a website called CFD Online. That's actually a pretty good one as well. It's got a lot of resources in it. I'd look there. Another question is, what's the maximum temperature a typical blade servers and other IT equipment can handle for proper operation? We assume in this modeler, mostly we assume 20-degree deltas. So 20 degrees, in order to, the basic, again, equation that I showed earlier, which is heat transfer is equal to mass flow rate times density times specific heat times delta T, shows that for 1 kilowatt, if you're going to try to reject 1 kilowatt of heat away from a server like that, you need about 156 CFM for a 20-degree assumption of rise across it. Most equipment, it's safe to use 20. Now, a lot of these new servers are claiming 30 and a little higher, but that's being a little aggressive. 30 degrees across a server, yeah, they can handle it. Do you want to run there? You can certainly try it with it. The program, CoolSim, is adjustable. You can adjust it to 30 or whatever you want. I tend to run 20. What do you think, Magnus? Do you have an opinion on that?
Was the question how hot it can be on the inlet?
Well, it's the delta T across the server. We are assuming 20. As you know, a lot of these new manufacturers are claiming they can run 30. But
oh yeah, they can be higher than that. I mean, if you have really dense servers, blade servers, it can be 40. Mm-hmm. Yeah, absolutely.
You can set it anywhere you want. It is programmable on the modeler, and you can start off with 20 and see what it looks like, and then go 30 or 40. The only thing that's going to happen is you're going to be pushing a little bit your reliability. Just a little bit more. Certainly the simulations we ran just now would look a lot better if I assumed 30 instead of 20 because the hot air would be hotter, of course, going back to the other side. So you can set it for whatever you want. We generally default to 20, but if you want to set it higher, it's all programmable. You can certainly set it anywhere you want. Mm-hmm. Well, we're up on the hour now, Magnus. It's been 1 hour, and we have covered most of the questions that people have typed in. Right. Again, I am recording this, so if you would like to review it again at another time, you can. I've got our contact information here for you. So if you'd like to get a hold of either one of us, Magnus or I, the email address is on the display in front of you. And I would like to, for those who attended today, just thank you for attending. If you want a certificate of participation for 1 credit hour of professional development, send me a note to this email address and I'll get one out to you. Any final words, Magnus?
No, I think you did a really good job demonstrating the optimization here. And I don't think, one question was how many iterations do you need to do? And I think that when you have your base model already in the computer, it doesn't take long time to run through some iterations like you did and look at the summary tables and look at those parameters, those 4 metrics. And very soon you're going to have a much better solution than you had from the beginning.
That's right. In terms of time to simulate, the simulations I ran for this webinar, each run would take in the range of 20 minutes to run. The smaller model took a lot less than that. The bigger model took about 20-25 minutes to run. You can run multiple variations at once, and those all run concurrently. So again, it's 20 minutes to do those turnarounds. So you can do this fairly quickly, and you can gain an awful lot of insight about the design and how to improve it. It's something that I think all people should have an idea in their data center of where they stand with respect to capacity or failure mode analysis. What happens if you take one of these units down for cleaning or cooling, or it fails. As well, optimization, what's the best place to be running at? If you know what the optimal point is for your data center in terms of operating, or at least have a feel for where that is, then you'll have a much better opportunity to save some money and also know where the limits are with respect to load as well as failure mode. All right, well, thanks everyone for attending today, and we look forward to doing this again in another couple of months. Thanks.